Alright, in this video we're going to talk through the method of integrating factors to solve a differential equation. So I'm going to assume that we have a first order differential equation that looks something like this guy. I've got y prime equals some function, y prime plus some function of t times y equals some function of t. Now these functions here could be constants, they could be trig, they could be exponential, they could be linear, they could be whatever. Doesn't matter. The idea is this, and it's relatively simple once you see it. Turn the left-hand side into the derivative of something. That's really what we're going to do, is we're going to just turn the left-hand side into the derivative of some function. And we do this by introducing what's known as the integrating factor. So the integrating factor, we're going to define that guy as rho of t equals e to the integral of p of t dt. Now, this seems like it's kind of out of the blue, but if you think about how the product rule works, this actually is beautifully simple. So if I multiply both sides of the original differential equation, by this integrating factor, I'll have y prime times e to the integral of p of t dt, I'm going to be very thorough here, plus p of t times y times e to the integral p of t dt equals q of t times e to the integral p of t dt. Well, okay, the left-hand side now, if we think very carefully about this, there's a plus sign sitting here, which just tells me from basic calculus maybe the product rule has happened to this. Maybe this is the result of the product rule. So, as a sidebar, let's just recall that the product rule is d by dx of f of x times g of x equals f times g prime plus g times f prime. Okay, so I'm hoping that the left-hand side of my differential equation is the result of the product rule. And indeed it is, by the way we've constructed our integrating factor. What we've got now is d by dt, notice the independent variable that I'm using here, of y times. Now let's just be careful and think about what I've got. Let's see, if I do e to the integral p of t dt, let's just check that. Right? If I look at this derivative, I'm going to say first times derivative of the second. Well, the derivative of the second it's an exponential, so it is that integral, or e to the integral p of t dt again, times the derivative of the stuff that was put inside the exponential, but the derivative of an integral is the thing inside the integral, plus second times derivative of the first. Indeed, this is exactly what the left-hand side was. And so by introducing this integrating factor, this guy right here, this funky little function, this rho of t, and multiplying both sides of the differential equation by that funky little guy, we can turn the left-hand side into the result of the product rule. Okay, what good is that? So let's at least look at what this turns into now. So the whole differential equation now looks like d by dt of y times e to the integral p of t dt, that's our integrating factor function, equals q of t times e to the integral p of t dt. I'm going to simplify my notation now and just say this is really d by dt of y times rho is the integrating factor, equals q times rho. And since the left-hand side is a derivative with respect to t, I can integrate both sides with respect to t, and I have y times rho is equal to integral of q times rho dt. One last step, and I have my solution. I have 1 over rho, times integral q times rho dt. And note well that this is a indefinite integral, and so there will be a plus c that comes out inside here somewhere. Okay, so let's run an example. All right, hopefully you followed everything so far. Let's just do an example. This is an example that you could actually solve with some other technique, and that's perfectly fine. In fact, what I want you to do is that I want you to pause, put this video on pause, go do a different technique to solve this differential equation. You know different techniques, 2 of them as a matter of fact, to solve this differential equation. Go do them. Go get your answer. Now that you have your answer, let's play this with integrating factors. So the integrating factor, rho of t, is e to the integral of 2 dt, because that p of t function is a constant function this time. My q of t function also happens to be a constant function. Right, well, I can do a little simplifying here. Let's see, integral of 2 is 2t, so this is e to the 2t. And notice I did not put a plus c on that. The plus c is going to come out in the wash at the very end here. I multiply both sides of the differential equation by e to the 2t. So we got e to the 2t times y prime plus 2e to the 2t times y equals 7e to the 2t. And I recognize that the left-hand side is the result of the product rule of y times e to the 2t. Pause and verify that if you actually do the product rule on this, that you will get the left-hand side of the differential equation from the line above. Okay, now that you verified that, I'm trusting that you put me on pause and verified that. Let's just push through the rest of the algebra. If I integrate both sides with respect to t, the derivative and the integral cancel each other by the fundamental theorem, second fundamental theorem of calculus. And over here I have integral 7e to the 2t dt, which integrates nicely, which is 7/2 e to the 2t plus a constant. Right, notice my constant has come out now. All right, so y times e to the 2t is equal to that. And one step of algebra and I have my solution. Oops, let me try that again. My solution is y is, I'm going to divide both sides by e to the 2t. And so I get 7/2 left out plus c e to the minus 2t. With a little bit of algebra. And then, of course, if I had my initial condition, I could go find the c. Okay, let's do one more example. Let's see here. So we've got this time y prime, not equals, plus 2ty equals 7. Very similar to what we had before, but this time I have 2t as the p of t function, and 7 as the q of t function. So my integrating factor, rho of t, is equal to e to the integral of 2t dt, which is e to the t squared. And multiplying both sides by the integrating factor leaves me with e to the t squared plus 2t e to the t squared y equals 7 e to the t squared. Recognizing the product rule, remember, we set up the integrating factor so the product rule happens this way every single time. There's no way to flub that up. It's wonderful. Integrating both sides. All right. Sorry, my software is arguing with me here. Okay. So I've got 7e to the t squared equals integral 7e to the t squared dt. Now something really interesting happens. This particular integral doesn't have a nice closed form solution. It doesn't have an antiderivative that we can just write down algebraically. So I say at this point we're a little bit stuck. Right? Since we don't have a nice antiderivative for this. And go ahead and try it. Think about U substitution, think about integration by parts, think about direct integration, any integration technique you can think of, try it out, you're stuck. The moral of the story here is that sometimes the integration that results from integrating factors is really, really nasty, so you have to think ahead to think whether or not you want to use integrating factors. Anyway, that's the end of the video. Best of luck to you.